I come from Peter Van Loop's group in Mainz, and what we're trying to look at is a completely classical communication channel with the idea of imposing some sort of a quantum component to it such that it shows an advantage in some regime. So, for example, if you have any classical communication channel, then we fix some constraints. For example, you can fix the modulation format or some detection schemes like homodyne and heterodyne. And what you can do is you can use some quantum component for squeeze, for example, squeezing, and try to find out these particular advantages in the regimes that you can get. That's the idea. And the later part of the thesis, we designed explicit receivers for showing some sort of advantage. So, for example, in single mode case, it's like if you have coherent state modulation, then the idea is to have optimal state discrimination between those two states, plus and minus alpha, which are not orthogonal. So we try to design these explicit receivers that achieve the Hellstrom bound. And in terms of multimode case, then it's not really the Hellstrom bound that's the metric, but it's the capacity. So for multimode cases, we try to design receivers that attain super additive capacity. Yeah, that's what.
Okay, thank you. So, Atin is stating.
Good afternoon, everyone. My name is Atin. I'm doing a PhD at the Brazil Davis group here in T. Braunschweig. So, the poster I'm presenting here is titled Quantum Communication System with Entanglement Budget. So, what we consider is entanglement assisted communication system, but we assume that the amount of entanglement, patient entanglement, is budgeted. That means it's limited. So, initially, you start with some amount of pre-shared entanglement, and when we start communication, and then the transmission and generation take place simultaneously, and then we look at whether the entanglement, the pool of entanglement bits get exhausted. We look at the probability, outage probability, and then once the amount of entanglement bits is exhausted, then we have to wait some more time for generating those required minimum of entanglement bits. So we look at that period as latency, and we look at latency periods, and basically that's it. We look at the outage probability, the latency of the system, and the efficiency of the system like that. In terms of that, yeah. Thank you.
Yeah. So my name is Benjamin Bayer. I'm from TU Munich, Professor Wolfgang Keller's chair. We're actually doing a lot of 6G research, and the quantum communication is just my topic, and I'm basically the only one person doing it at this chair. And we're basically looking at quantum networks from the networking side of things. And here what we did is we looked at the single link. We have like 4 different methods to establish entanglement between 2 different nodes. And the question is now, how does the networking protocols look like? What kind of classical information do you have to transmit between the 2 nodes? And we developed 4 protocols for that. And on top of that, we have the purification protocol. So we establish multiple entanglements between, or simulate multiple entanglements between the 2 nodes, purify them, and look at then how is the fidelity, so the quality of the entanglement, how is it after the purification, and also the delay, basically how long does it take to establish that entanglement. And this is really important. These are basically analytical models for simulations. And based on this, you can then do like large-scale simulations with 100,000 nodes separated by vast distances. So actually the goal of quantum communication.
Hello everyone, I hope you feel good. I'm working on oblivious transfer, and before everything, I have to say that I'm a PhD researcher on this Christian Data at the Technical University of Braunschweig. This is my PhD thesis, and the goal is to finding the answer to this question: that does entanglement chain is helpful in an oblivious transfer scheme or not? So if the answer is yes, how can it be possible to do that? So for the first step, we have investigated the limits of oblivious transfer from the perspective of information theory for various types of channels, such as multiple access channels, point-to-point channels, and for various types of nodes, for example, dishonest nodes, semi-honest nodes, semi-dishonest nodes, semi-malicious nodes, and fully malicious nodes. So if you are interested to know more information about continuous transfer, I will be ready to discuss with you.
Thank you.
Yeah, so I'm presenting mostly for Simon and Karim. It's about QRead, that's a simulation system which you can use. And of course, we try to do many things better than they have been before. So quantum simulations allow you ideally to do hardware and architecture prototyping. Oftentimes the simulators are too general or they are too specific. They don't have a graphical user interface, so the models are not really accurately reflecting the experimental reality, or the design is not useful in the collaboration with colleagues. And we try to make some of these things better. We have accurate simulation time. We have the possibility to model just any Hilbert space, in particular Fox spaces, so you can model optical systems. You can include physical quantities such as pulse width and pulse shape. The components that are used in the simulation are interoperable, like a Lego, but they obey physical laws. You must list properly what is the physical meaning of each in or output to a component. And there's a graphical user interface, so you can have some visual impression of what you are building, and you can share this with colleagues which are supposed to probably build your machine, so they understand what is coming at them. And we hope to have an accelerated development of quantum technology using such simulation tools and bridge the gap between theory and implementation. And the most exciting thing is you can be part of this. You can submit components yourself. We are organizing a special issue with advanced quantum technologies, where you can submit original articles which provide these exact simulations, hopefully with some numerical and mathematical guarantees on the errors that are introduced by, say, various levels of accuracy in the simulation, and together with ideally some concrete parameters where the system was actually tested in a lab, so that other people can at least maybe rely on the component when they are prototyping something. And with that, you can become part of the QRead community. Okay, thanks.
I'm Jerry Horgan from Trinity College Dublin, and I'm looking at QKD metrics, systematic metrics for QKD networks. There's a lot of QKD experiments out there, both in the lab and on plant fiber, and you get lots of readings off of these, but you get usually you get a secret key rate at a particular distance or something like this. If there's coexistence, you might get, if there's classical channels there, you might get a QKD, and that's secret key rate at a distance with a particular launch power. But how do we compare these metrics? All the experiments are different. Sometimes they're set up to address a particular thing. They could be using different types of fibers to eliminate noise. They can be using different channels, different bands, different wavelengths, different types of detectors and stuff. So we get this wide variation in these experiments and in these metrics, and we haven't found a nice way to compare things. So we're working on that metric right now. Part of what we're going to do is we're going to run a series of systematic experiments whereby we go through each kind of scenario, each power level, each loss level, and so that we can normalize out this loss over time, so that we can try and determine the difference in the experiments, who's made a practical large-scale improvement in a QKD system versus a tweak in the experiment. And we're also trying to then find the margins that are available in QKD networks to deliver a proper secret key rate at a particular distance.
Hi, I'm Johannes Rosenberger. I'm working in the group of Holger Boche at TU Munich, also working, for example, with Christian and other people here. My poster is about identification over quantum broadcast channels. So probably many people here don't know what identification is. It's a communication problem where instead of decoding a message, the receiver also has a message and asks, is the sender's message the same as mine or not? But the sender doesn't know the message. So, for example, in some sensor, like if the receiver wants to survey some sensor states or something, they send it and the receiver just checks is everything fine. And in this setting, when one considers broadcast channels, where there are two messages and each is for one receiver, but you want to pack them in one channel input, quantum channel input in this case, then the question is how to pack the two into one quantum state. So is there some interference between the messages or not? And also in general for identification, the question is the performance different? Is it better than for transmission? It turns out that both is the case. You can compress super efficiently for for identification, and also there is less interference between the encoding of the different messages. And so for classical quantum channels, we have really a rectangular rate region per input state, like average input state. So if you want to see more, you can look at our cluster, and there you can also see how we prove things, and we can discuss possible extensions to this, for example, to fully quantum settings.
Hi, my name is Jonas Havlik. I'm from Clifton's group here at TU Braunschweig, and I currently work on the completely classical interference channel, but I'm still here today because we introduced some entanglement between the transmitters and want to investigate how this can help with increasing the communication rates. And yeah, therefore I consider rate regions, which ended up to be quite similar to the classical ones. So we have somehow to show the advantage of the entanglement, and therefore I further investigate some channel examples based on so-called non-local games, for example, the Magic Square game. And for these, it's possible to show an advantage. And yeah, you can take a look at my poster to see the details. And I would also like to discuss with you in general the role of these games for this problem, and how to maybe find some more practical channels where this advantage is visible. Yeah.
I'm gonna talk also about identification. It's the problem Johannes discussed. I'm gonna look at deterministic identification for quantum and also classical channels. Deterministic identification is the kind of identification where you don't use randomness in the encoding. We discuss some strong verifications. And yeah, it's a fun journey. It's very curious. We start with quantum, we move to classical, and then we go back to quantum. So if you want to, yeah, so I see some strange and puzzling results, some links between quantum communication and fractal theory, some subreactivation results for classical channels in naivety, memory, aesthetics. Just top secret, we will discuss about that.
Hi everyone, I'm Shivam and I work with Ricardo at T Preston. This work that I'll be presenting today as a poster, it's a very preliminary work, and it's basically me presenting a novel idea. But I think it can be interesting for two reasons. First of all, for this particular work, we are trying to use entanglement as a resource for classical communication network for a very particular problem, in this case, a decision-making problem for a BNF migration scenario. And second reason it could be interesting is that it basically utilizes entanglement to ensure anonymity in a communication network, which is an aspect of trustworthiness, or it relates to security, but has not been explored a lot, or it has not been explored as something which could be ensured using quantum technology. So this could be an interesting new point to discuss through this particular poster. Thank you.
Good afternoon, everyone. We've had a lot of interesting talks today highlighting the importance of long-range quantum networks. However, a recurring theme has been the bottleneck caused by quantum repeaters or their lack thereof. But given a quantum repeater of the second generation, which can accommodate active error correcting mechanisms, which quantum error correcting code do you use? In my master thesis project under Christian Depe. I will be addressing this problem. In my poster here today, I plan to showcase some preliminary results addressing the same question. I'm excited to share the results with you. See you there. Thank you.
Okay, so my name is Albert. I'm in Krakow, in Poland. So, okay, to implement a quantum channel, non-local quantum channel, bipartite, for example, we need some non-locality, some non-local resource. But this resource can be spoiled by decoherence in different ways. So what we do is we quantify this resource of this resource of non-locality for channels, not for statements, for channels. We identify a portion of non-locality that survives after the coherence occurs, and what we do it by identifying as the non-locality of something called the classical action of the channel. We can learn about it later. And the results is that, and the results are that we find that very surprisingly this portion surviving the coherence is relevant for quantum protocols even in the absence of the coherence. It's needed for optimal performance. And we have also some simulation results of stochastic processes. The project is divided in 2 papers, so 2 posters, both presented in the same area. Thank you.
Good afternoon, everyone. My name is Anshu, and I work with Yanis. Today, I will be presenting about discrimination of binary coherent states using the linear receiver that uses an adaptive measurements. And the motivation to work with this was, can we achieve better, or can we reach Helmholtz bound using the size coherent states? We use generalized measurements, which is a composition of minimum error state discrimination plus unambiguous state discrimination. Further, we also found out the optimal displacement waveform using the X derivative, because we are working now in discrete waveforms, and later we compare the correct probability of correct detection, error, and inconclusive measurement, and compare it.
So I'm Florian Satz. I'm doing my PhD with Yanis at TU Munich. And the poster today is about classical quantum communication channels that have some uncertain channel parameters, which we call compound channels. And so the idea is, how can we deal with these channels to send maximum information about over them? And one way to do that would be to just try to learn these channel parameters first. The problem with that is it takes time, it takes effort, and you need feedback. So an alternative is using a compound code. And what that does is basically just say, okay, we deal with it, we can still send some information, even if it is not at optimal rate, but we can just start doing it right away without waiting. That's compound code, and I will argue a bit more why that's a great thing. And the way we realize it is by using sequential decoding, which is just a way of decoding where you don't perform a single measurement for all the possible messages, but you ask one by one, is it this message? No. Is it this message? And in that way you keep going. And this is particularly practical for the compound channel, because you can just combine the question, is it this message with this kind of channel, or this channel parameter, or this channel parameter? And in that way you can learn the parameters of the channel as well as the message at the same time. Thank you.